Hi. Hi, everybody. Wow. Put monads in the title and everyone shows up. Never fails. Oldest trick in the book now. Okay, so today we're going to talk about what have the monads ever done for us. If any of you are here thinking that you need to know monads for functional programming, I can save you a lot of time and say you don't actually need to understand them to get a lot done. However, if you want to understand them, I will endeavour to enlighten you a little bit over the next hour or so. They're not as hard as everybody makes them out, and in fact the reason I wrote this talk was there's a lot of mysticism built up around monads and a lot of stuff involving category theory and all of that. And you can get a pretty good grip of them just by following the money, I guess, would be sort of the analogy. Just following the facts and seeing what they have in common, what attributes they have, and that sort of thing. We will cover the laws because they are important, but they're also fairly simple. So, okay, quick bio on me, and I will keep it short. I have a partnership with Bill Venner's Escalate Software. We actually do the Scala training for the Parlays courses now. Took a little bit to get on. The applied course is up there now. The advanced course, which actually covers more about monads and a whole bunch of other stuff for library and API developers, will be up later in the year, hopefully. Around Christmas time is our aim. I also wrote a library called Subcut, which is a dependency injection solution for Scala, and I contribute fairly actively to Activator, TypeSafe Activator now, and also develop a lot of templates for Activator. It's one of my favorite things to do. It's nice, quick open source projects that benefit people directly, so I like doing those. Some of you may know I co-host the Java Posse and also the Scala Wags podcasts. So, all right, and as you can probably guess from the pictures up here, hello, I can't resist. Every time the photographer comes in, I have to say hi. The Monty Python and the Life of Brian had a scene in it where the somewhat dejected people of Judea, or Judean People's Front, I can't remember which it is, are sitting around complaining about the Romans. And they're like, what have the Romans ever done for us? And it gets to the point in the conversation where he says, all right, but apart from the sanitation, medicine, education, wine, public order, irrigation, roads, freshwater system, public health, what have the Romans ever done for us? Brought peace? Oh, shut up. So the idea of this is that while you may not be necessarily aware of monads, if you've done any functional programming, and in particular if you've used Java 8 Streams API, you're actually taking advantage of them right now, and in a number of other areas as well, and we'll see those as we go through. Why should you care about monads? Well, honestly, you shouldn't really. If they're working for you and you're already happy and already using them, then you really don't need to care that much. But people are interested, so I figured try and put something together and give an idea of what these things really are and how they work. A lot of people claim they're a silver bullet. I've been programming, 25 years now, maybe, something as long as that. I've never seen a silver bullet in all that time. I've seen many that have claimed to be. Without fail, they're never silver bullets, but also without fail, they usually have something interesting about them. And so when people say it's a silver bullet, it's probably worth looking at and seeing if there's anything useful there. So, let's start out simple. We're going to start out, and I'm going to use the terms because originally I didn't use these terms. I thought they were too scary for people, and what I've decided is it's just a name. I should have had the slide on this one. I started putting up pictures in our training of an okapi, which is an animal. I don't know if any of you know about the okapi. It's like a half zebra and half giraffe. It's a weird-looking creature, really interesting. And knowing it's called an okapi tells you absolutely nothing about it, okay? Similarly with these terms, they're just names. Don't get hung up on them. But you've got to refer to these things as something. We have to have a name for them, so we're going to start out with them. Now, monoid is a true mathematical, an old mathematical term and a mathematical concept. Roughly, a monoid is an accumulator. It's something that is able to join or accumulate things. And the characteristics of a monoid are that it has a starting value and some kind of function to combine values together. An example of these are, for example, addition. the starting value would be 0. It's also sometimes called 0 or identity. None of these terms are really ideal because it's not always 0. And, identity's closer, but yeah, anyway, so addition, the starting value of 0, and the combiner is plus, a plus b. Multiplication, the starting value is 1 in that case, so 0 value is a bad name for that. And the combiner is times, product. String concatenation, an empty string, and you concat the strings together. And a list concatenation, list nil is the empty list, and the combiner is concatenation, like that. Now, interestingly, and on the next slide I'll talk about this, minus and divide are not monoids. They're not true monoids. And that's not because they lack anything here. We could define them using these properties. But there are also laws that go with monoids that make them into monoids. And those laws are, if you take some value, I don't think my, it is working, but it's terribly, terribly dim. If you take your value and apply the starting value to it, through the combiner method, you should get back your starting value. That's why it's sometimes called identity. And likewise, starting value applied to our value with the combiner function should also give us our value back. Those are true for divide and minus as well. The next one isn't, though. The next one is that given three values, applying the function to A applied to B and C grouped together should be the same as applying the value to A, apply B, and then apply C. And if you do that with minus or divide, it doesn't work, so it violates that law. Therefore, it's not a monoid. Everybody with me so far? Yeah? Okay, do stop and ask questions along the way if you feel you want to. There should be time for this. It took 45 minutes to do it before, so hopefully there'll be time even for the demo at the end. Okay, so how can we write a monoid? Let's take a look. And all of the first two-thirds of my talk, I was going to say all of my talk, but actually the first two-thirds of my talk, the examples are using Java and Java 8. And it's only in the last part of the talk that I actually move into Scala, and that's to show some of the more advanced features that you get there that make things look a little prettier. But particularly with Java 8 having lambdas now, you have the power to use, you've got the full power of monads available to you. So here's a monoid. Very simple. It's genericized by t, type t, and we have a starting value of t, and we have a combine method that takes two t's and returns a t. Okay? That is our interface. Now we can implement that, and we can provide an addition monoid, which is the one we saw. The value for that is 0, the starting value is 0, and the combining value is a plus b. We can have one for multiply. So again, you'll notice the type signature of the inheritance. This is int add monoid. It's a monoid of integer. This is int mult monoid. It's still a monoid of integer. Okay, type signature is the same, but the implementation is different, obviously. This time, we're starting with a value of 1, and we multiply numbers together. Okay, now we can have a combiner method, and this is where it starts to get interesting. So now we've actually defined this thing that is our monoid, this way of accumulating values together. Now we can use it, and we can make it generic, and this is where it starts to become interesting, because what we're taking is the first steps into something called generic programming. This is where instead of writing something that just adds up numbers now, we can say, I'm going to combine this list of numbers that I've got using any kind of monoid that's defined. And that means that we only have to write this method once. We don't have to rewrite it for every time we want to do a different operation. So here is a combined list. It takes a list, and this is genericized. So it takes any list of t's, okay, and a monoid of t. Okay, and then basically what it says is if the items are empty, then you just return the starting value. That's the easy option. Otherwise, you get the first item, and then you iterate over the remaining items, and you call the combiner repeatedly on those items and return the value. Right, all good? Pretty simple so far, I think. Don't worry, it'll get going faster in a minute. Okay, so in use, let's see it. We've got a list of integers here. We just made an array into a list. And now we create the monad. Oh, I put this in a I didn't show it, but these are in or this would be defined in like a monad demo implementation, something like that, so that you've got the things that you need. Anyway, so monad demo impulse is a new monad demo impulse instance. And then we can say combine list, and then give it our list, and we can give it our add monoid, okay, and it adds them up, 55. And then we can do the same thing with the mult monoid, and this time it gives the product of all those numbers together. So it works, very simple. And even nicer is if we want to do strings now, we can now make a string concatenation monoid, and I showed you before, that's an empty string and string concatenation. And then we can call that on an array of strings now. So we've got one method now that we've defined that can combine any list of things, provided you've got a list of the right type and a monoid of the right type. Good, okay. Don't see anybody throwing their hands up in despair yet. Okay, so let's move on to the next one, functors. Another great name. They have such good names. They're really satisfying to say, and they make you sound smart. It's awesome. Just talk about monoids and functors for a bit, and everybody's like, ooh. So, what is a functor? Functor roughly is some kind of transformer, and in particular, it allows you to map a function over its contents. Okay? So you've got something that holds on or encompasses, you can think about it as just a container, but that's not a broad enough definition. That's the problem that you get. This is really what the problem is with all this category theory stuff, is the categories are so broad that the minute you start to say, oh, it's a container, you've immediately cut down the actual useful domain that you're working in. So a functor is anything that allows a function to be mapped over its contents. And what you care about is it has a map method. That map method takes a function and it returns a new thing of the same kind that has the contents transformed by the function you passed in. So let's say in Java 8, and we'll see this, in Java 8 you've got optional. Okay, if it's got something inside of it, let's say it's got a 4 in it, and you map a function that multiplies numbers by 2, you'll end up with an option of 8. That's all it is. Okay, let's have a look at the linked list. I'm actually going to implement this. It's not a perfect implementation. I'll get to why along the way, and I need to update the slides because somebody sent me a really nice way of doing this. But we're going to create a dead simple list. If you ever create one of these, it will perform horribly. Okay, it's not meant as a performance example. This is just meant as to illustrate the concepts, and it's as simple as I can possibly make it. But here's the thing that makes it the functor, is the second line in this. Public abstract U, generic U, dead simple list of type U, and it's a map function that takes a function from T, where our dead simple list is genericized on T. It takes a function of T to U, and it returns another dead simple list of type U. Okay? So we can change types. We can change the inner type. If we've got a 4 number, integer, we could change that to 4 stars with our function, and then we'd have an optional or a list of string. Okay? The other thing I'm going to show you, just implementation details, but they're quite neat, is there's an isEmpty method. All of these are pure virtual, so they all have to be, this is a pure virtual class. Anything that implements it will have to fill in these methods. So isEmpty is going to tell us whether the thing's empty or not, and contents as a string is just so when I show you the demo, you can actually see the results printed out. Okay, so now let's do the implementation of our dead simple list. Here is a dead simple list nil, okay? Now, I think it's time to introduce another concept, which is a really nice one, and not too scary. Algebraic data types. These are tremendously useful things. They're used all over the place, not just for functors and monads and stuff like that. Basically what it is what we just saw. Usually it's a very generic and abstract top-level class, and then underneath it are a finite, usually small, number of concrete implementations. And when you get that arrangement, it's known as an algebraic data type. It's like a set of things that you can use. So this is a list is an algebraic data type. Okay, there's 2 basically two things that you can have in a linked list. You can have a nil, which is an empty list, or you can have an item followed by another list. Those really are the only two options in a dead simple linked list. That's all you need. So it's an algebraic data type with two things. They're traditionally called nil and cons. Cons is the construction of a list. So this is our nil. The nil map is dead easy. Okay, we're empty. So what do we give back? An empty. Okay, we take the function. It's there to satisfy the type signature. We don't do anything with it. We simply give back a new list that's genericized with the new type that we've got. We don't have to apply anything at all. Another nice thing that you end up seeing all the time with algebraic data types is things like is_empty usually fall out to being nothing more than a true or a false, or an incredibly simple implementation. Okay, a nil is going to be true. It's empty. That's always the case. And the cons is always going to be not nil. It's not empty. Sorry. So that's always going to be false. And then finally, we print up the contents as nil. The non-nil is simply a head, an item at the head of the list, followed by a tail. And the tail could be another list, another cons, or it could be a nil. Okay? If we've got an item followed by a nil, that's a single length list. And if we've got a list followed by a million other cons followed by a nil, then that's a million long list, or 1,000,001 long list. The point is that every list ends with a nil, and you can build up these things basically very simply, very simple linked list. Now the map in this, what we have to do, we have to satisfy that map, and there it is, map function from T to U, and that's the function, and we need to return a dead simple list of U. What we do is apply that function to the head, and then we do a tail map. Okay? We just use recursion. Dead easy. So we apply the function to the head, map the tail, and we cons them together, and we get a new dead simple list of type U. As I mentioned, is_empty on a non-nil list, on a cons list, is always false, so that's easy. And then the contents as a string is simply our item, head, as a string, and then that : is just a cons operator. That's a convention that's used in a lot of functional languages. So that basically means our head followed by the tail, and the tail we just recursively call contents as string again. All right, so very simple. Anyone lost at this point, or no? Yeah, question?
Why isn't that an interface rather than an abstract?
Oh, this one, it could be an interface. I haven't been programming in Java for a while, so I'm a bit rusty. That should probably be an interface, yeah. No, there's no magic there, no. No, you're quite right, that could be an interface. In Scala, I would have made it a trait, but, I'm just, like I said, a little bit rusty on my Java. So, a list example, using it. This generates a dead simple list called getNums, and all that does, this is largely just implementation details, but it conses a list together based on, one thing I will point out is you start from 10 and you go down to 0, and that's because when you're building up a linked list, it's much more efficient to put new items at the head. So we start at the end and we work backwards until we get down to 0. So that's why that's like that. And then a method down here called string number of stars. It takes an int and returns a string, and then basically what it does is just gives us that many stars back. So if you start with 4, you get 4 stars back, and if you start with 2, you get 2 stars back. And then if we actually use this, we can say now, here's our simple list demo support. We get the numbers. We can print out the numbers. So you see there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, nil. It always ends with a nil. We can map the function x to x times x over it, and we get back a new list, because the other thing about our list is it's immutable. Everything in there was final, and the original list won't change. And that's also very important for functional programming. So we get back a new list with those in, and if we use the method reference, first time I've used a method reference in Java when I was writing these, it's kind of cool, just to say the number of stars, that is a function from int to string. So now we actually get back a dead simple list of string rather than a dead simple list of int. Okay, that's a functor. That's all there is to it. It's got a map. You need a few more details, like you need to be able to put things in it and stuff like that, but the map is what makes it a functor. All right. So here's another functor. This is actually from the Java 8 libraries. This is from the source code of Java 8. The only thing I did was remove the wildcards because they really made it hard to read. And I just thought, you know, it's unnecessary detail. We're not here talking about wildcards. We're here talking about map. So there is that function. One of the things I haven't, or that map method, one of the things I haven't really mentioned yet is map, the name, is just a convention. What really matters about it is the type signature, okay? That type signature that says, I am, you know, some type M genericized by T. Given that, if I have a function from T to U, map, or whatever we call this thing, will return an M of U, okay? That's our type signature. Take a function of T to U, return an M of U, okay? And that's what this is doing. So what we get here, M in this case is optional. It's genericized by T. And again, that is exactly the same type signature that we were looking at before. The map takes a function from T to U, that's the mapper, and then it returns an optional of U. And there's the implementation. There's a bit more in this one. It requires that it's not null, so mine didn't do any null checks, because I'm out of practice at that, because we don't use nulls in Scala. That's dangerous. So, and it says if it's not present, then return an empty. Otherwise, return an optional of the result of mapping that function over the value. And then there's this other one here, flat map. And I'm going to get into that a little bit in a minute. Now, the thing to look at with flat map is that instead of a function from T to U here, flat map is a function from T to optional of U. Okay? I'll come back to that in a minute. But all that does is, instead of saying optional of nullable of the result of the mapper apply, it applies the value and it just requires that it's not null. Okay, so this actually produces an option U, and overall we still produce an option U out of flat map. All right, let's go over the functor laws really quick. I'm not going to spend a lot of time on them, but these are the two, as well as having the map operation, in order to be a true functor, you need to satisfy these two laws. The first one is that if you have an ID function and you map the ID function over the value, you get the value back. Pretty easy. Okay, so if it's, you know, +0 is the map for integers, or the ID for integers, then applying it to 5 should give you 5 back, if your map is written correctly. And then the other one is the composition of two functions. So if you say x map a and then b, which is the composition of those two functions, that must be the same as saying x map a, and then on the result of that mapping b. Again, it's pretty obvious when you stop and think about it. But these laws are impossible to actually ensure programmatically. So what you have to do is do the mental exercise of, you know, have I satisfied that law? There are runtime ways you can do it, things like Scala check. There's these various libraries out there that will fire all sorts of values at it and make sure these laws hold. But generally the way that you do it is you kind of rewrite the code, actually rewrite it based on expanding out the code that you've written for your map and make sure that they come out to the same thing. All right, so what is this flat map? Well, the flat map is what makes this thing a monad, along with one other thing that I'll talk about in a minute. If we were to take our map operation and apply it to a function from A to B, okay, then we get back an option of B. If we apply it on a function from A to option of B, then what we get back is an option of B. Okay, we've gained a level of nesting of this thing. So what a flat map does is it has a type signature that says lose that nested type, lose that nested monad. It's got to be the same thing. It's got to be the same kind of container, but we only want one of these containers, not two of them, not one inside the other when we finish. And the semantics are really simple. In the case of optional, the semantics are if you start with nothing, if you start with an empty, you end up with an empty. If you start with an A, an actual value, and your function maps from A to empty, you end up with an empty. And if you start with an A, and your function maps from A to container of B, then you end up with a container of B, not a container of B. That's the type signature. Okay, so that's what you have to satisfy. So, anybody with me or anybody lost at this point? It's entirely possible. That was a fairly big jump. If it seems too simple, then great, you're in good shape, because it really isn't that hard. But it's just basically, what it actually is doing is throwing away some information. Okay, we're actually taking this idea that there's two containers there, and we're throwing one of them away and just keeping it in the other one. It's like, I don't know, getting a box within a box from Amazon. When you send it back, you're like, I don't need this other box. You just take one of the boxes away. Okay? So that's it. All right, lists and collections. These are flat map implementers in the Java, well, actually in the Scala libraries and in the Java 8 streams. Lists and collections implement flat map. Streams implement flat map. You will have seen this if you've done anything with the Java 8 Streams API. There's a map and a flat map in there. Futures. Now, here's where it gets interesting. The composable, I think it's called composable future in Java 8. I'm blanking on the exact name, but I believe it's called a composable future. It has a map and a flat map in it, only they're not called that. They have different names. But if you remember, what I told you what's important about them is they have the right type signatures, and they satisfy the monad laws. So they are monads. Okay? It's just that they happen to be called, I can't remember which one's which, but it's then apply, and then apply async, and then compose. These are the equivalent methods. One of them is, if you want to do this as an exercise, look up that type signature that I gave you, which is basically m of A, given an m of A, and a function from A to m of B, you end up with an m of B. Okay? Find that type signature, and you've found your flat map. Try, which is in the Scala libraries, this is a hotly debated one because many people say it's not a monad because it violates one of the monad laws. It actually only violates one of the monad laws if you use success rather than try as the constructor. So, we go back and forth on this. But the point is, and we'll show you this in a bit, you can still flat map over things that aren't necessarily monads. There's nothing to stop you doing that, it's just a function. And in fact, they're still very useful when you do that. And of course, you can roll your own, and towards the end, we'll have a look at what some of the custom ones are. Right, so a Java 8 streams example, let's have a look at this. This is a simple one, this is just a functor. So we're using here, actually it's a functor and a monoid combined. So now you get to see how these concepts start to build up. So here we're taking our list of numbers, and we do a stream on it. We filter it, in this case. Filter is just something that collections can do. That's not a property of either functors or monads. It's just a convenient thing that we are able to do on these. Then we do a map. That's our functor. We do that's because it's a functor, we can do that. So we map, and we get the square of it. And then we do a reduce. And what have we got in the reduce? We've got a starting value and a function that combines two values into one. That's a monoid. So there we go. Reduce is another way of expressing a monoid. What we could have done, if there was a method for it, was just say combine there and hand it the monoid that mirrors that function that's defined, that starting value and function, and it would have the same effect. So there you go, and then there's all by all sum all combinations. Now this is where we get into the monad part of this. So the second one here, we take the list and we stream it, and then we flat map instead of map. And then the second thing, we get handed this I, this value, and what we do is we then take the list again and stream it again. So now we've got an outer stream, our box, our container outside, and inside of that, we've got a function that creates another container of the same type, in this case the stream. And so our function goes from I to a list of stream of the map of all those values multiplied by I. Okay? So we'll end up, when we do this, this is a map, so this is using the functor thing, but what that will do is take our I coming in from the from the outer list and multiply all of the values of the inner list by that, and we end up with a new list, but we still end up with a list. We don't want to end up with a list. We don't want to end up with a list of lists, which we would do if we had a map. We want to end up with just a list of all of these things concatenated together. So that's why we use a flat map, and then you say reduce, the same reduce as before. Now we get a different answer because we're multiplying all these things together and then summing them up at the end. Okay, so that's a flat map. It's a pretty contrived example, but it gets more useful, I can promise you. All right, so good so far, I think. All right. Optional, Java 8 optional, which is what we've just seen. You can do flat maps on these too. So here's the thing, here's where it starts to get interesting. Let's say you're looking things up from a database and you do one lookup and it comes back with a success. Okay, we got something. And then you do a second lookup based on that first one, and it could fail or it could succeed, so it needs to be an optional return again. But what we want out, we're not interested in how it got there. What we want to know is whether it could get a result or not, overall. So our overall result is going to be just an optional of the result. It's either going to be there or it's not. Okay? No matter how many levels, how many times, how many different operations we do that could fail, if any of them come back empty, the whole thing should come back as empty. Otherwise, we get the result in an optional. And that's what these are doing. So here we've got optional result is the optional result of all by sum, which was the one we calculated. We've got a doubler, which is an optional of 2, and we've got a not there, which is an optional empty. And we can do the same operation on all of them, which is to say optional result, flat map, and then in this one we do doubler map and the same function, and not there map and the same function. The results of those, the first one is that it's basically an optional, a sum, a filled out one with 3025 multiplied by 2, which is 6050. The second one is empty, because one of them was empty. And it doesn't matter if we started with not there and flat map the op result over, we would still get empty. Okay? That's the rules of that flat map. If you start with an empty, you end up with an empty. If you start with an empty and if you start with something and you go through a function that gives you an empty, you end up with an empty. If you start with something and you go through a function that gives you something, you end up with something. Okay, good. Right, now for the monad laws. We're doing really well, actually. So these are a little bit more tricky. What I did, and I'm not going to talk too long about this, but if you keep this slide handy or whatever, and if you want to come back and ponder this, treat it as sort of an enlightenment exercise afterwards. These are the implementations, kind of the rewriting implementations that show that for Scala option, these are true. So basically what we say is, and I didn't mention this, for something to be a monad, there's one more thing it has to be able to do. It's not just flat map. If you have a value, or a value of some type, there must be a way that you can box that thing into the monad, okay? And in Scala, that's called apply. In Java, it's called a constructor. There's various different ways that you can do it. Haskell calls it a point. All of these different kind of things that people use. But the idea is that if you've got a 5, there must be a way to obtain an optional 5 in order for this to be a monad, and there's got to be a flat map. So what we're saying here is applying the monad to x and then flat mapping a function over it is the same thing as calling function on x. Okay, that's the first rule. If it satisfies that, you're in good shape. No, it's not, because the function has to be, in this case for it to be a monad, the function has to be from a value to monad of the result. So, yeah, that's a good question, but the fact that you're asking that question means that you're grasping the principles at play here. So the function here has to be a function that takes an individual value and turns it into a monad of the result. And that's why that works. Okay? The second one, applying to x and then flat mapping apply. Okay, this is a little bit weird, but there's nothing that says the things that you throw into flat maps can't be functions themselves. That's the idea of functional languages. Other functions are just more data that you can pass in as parameters. So applying to x and then flat mapping apply should be the same thing as just applying that thing to x. Okay, and again, that is demonstrated down here. Sum is the constructor in Scala for creating an optional. So sum 5 and flat mapping applied to it actually does come back as sum 5. You can check that, and so it satisfies that law. And then the third one, this one's a bit more tricky. Applying to x and flat mapping f and then flat mapping g is the same thing as applying to x and then flat mapping, but you do this bit first. You flat map a function that takes x, calls f of x, and then flat maps g over it. And again, that works because the contents of an option can be a function. So, and that's demonstrated down here. So if it has an apply or a point or whatever you want to call it, something to box up this thing and make a monad out of it, and it's got a flat map with the right type signature, and it satisfies those 3 laws, it's a monad. Done. That's it. Okay? So, was there... Yeah, question? What's wrong with try? Try, good question actually. So try is a bit debated. Because what try is doing is actually capturing exceptions that are thrown. Exceptions are bad in functional languages because they disrupt the actual execution flow of a program, and that is not at all functional. That's a very non-functional thing to want to do. So when you wrap something in a try, if it finds an exception in there, it swallows the exception and returns a failure. Basically, one of these tries, which is a monad, it returns a failure state with that exception in it. So instead of going up the call stack, it's just got it kind of trapped like a fly in amber, and it just kind of passes it back out. The problem is, if you use success, okay, success is another constructor. Success assumes that there's not going to be an exception thrown. So if you use the success constructor, it violates the third of those laws. You get a different result back. So that, yeah, that's a very good question. It's in depth. But if you use try, it doesn't. So therefore, if you use the try constructor instead of the success constructor or factory method, then it is monadic in nature. So, okay, Scala lists bear a staggering resemblance to what we saw in the Java 8 streams example. Here we can see the Scala list basically almost identical. We start with numbers and we say filter and we look for the even ones. We map x to x times x and we do a fold left. The only difference here is that Scala has something called currying, which just means that our starting value, instead of being before a comma, is in a separate parameter list. That's just a trick it knows. Likewise, our all by all sums, the same thing. It's a flat map this time, so we start with nums, flat map. This is our number coming in. We get nums again. We map the result of multiplying those two together. Because it's a flat map, we end up with one big long list instead of a list of lists, and then we do the same fold left over it. Okay, option, Scala option, shown this a little bit. Sum is the constructor for something, and none is the absence, the empty one. And again here, exactly the same example, just written in Scala now. So all by all sum, this is our doubler, this is the empty option int. And if we flat map, if we do an up result flat map doubler, then we'll get back 6050, sum 6050 again. We do this, we get none. We do this, we get none. Okay, now this is where, see, looking at these, this is all doable in both languages. But looking at that, particularly the third one there, it's not instant, oh, I totally understand what that's doing. You have to reason about it for a minute. Okay, and this only gets worse as you get into like seriously chained composable futures with lots of flat maps or then apply asyncs and things like that. It takes a lot of reasoning. So Scala has this trick that it picked up from languages like Haskell. It has this language construct called for. And basically what it does is it takes all those chained filter, map, flat map, all those kind of long chain things, and turns them into a construct that's much more readable. But behind the scenes, all the Scala compiler does is apply some rules and change it back to exactly that form that you would have written otherwise. So for the mistake people make when they're coming into Scala, and it's a really easy one to make because let's face it, most other languages, for is a loop. So when you get to Scala, everybody assumes for is about looping. And that'll hold you for a little while because, you start looping over things. But actually, for is not a loop at all. For just rewrites things into map and flat map and for each and a few other things. And if it's not a list or, some kind of collection, it's not a loop at all. And you can use fors over futures and things like that. I'll show you that in the demo. So here's the Scala list using for, same thing as we had before. What we can say is, we need parens around it because we're going to call this sum afterwards. We can just say for n from numbers, or nums, if num is modulo 2 is 0, yield n times n, and then sum the result. Sum is just a convenient method that's provided for you on Scala collections. It does the same reduce operation that we saw, we just don't have to write it anymore. And it's a monoid, actually, funny enough. And then all by all sum f, this one just says for n1 from nums, n2 from nums. Now this is doing a flat map in between, but you don't have to see that. It looks very natural. What we're saying is, get me all the numbers from this one time, then get me them again, then yield the result of n1 times n2. Now looking at that, you think, yeah, I'm going to get back a list of numbers from that. It's going to be flat. It's not going to be nested. It seems obvious what it's doing, and it should be. So that's just a little bit of syntactic sugar. Likewise for the options that we had, same kind of thing. We can say for n1 from optional result, n2 from doubler, yield n1 times n2. This is a lot clearer than having that flat map and map and all that stuff. Same resulting code, exactly the same resulting code. It just looks nicer. And here's the third version where we have an optional result, the doubler, and not there, and that will come out to none. Okay, Scala future using for, and let me just see the try. I'm going to skip the future one because I've got a demo for that at the end, and we've got time to do it. So I'm going to do the Scala try using for instead. So here is a try. Okay, we're going to say try reading from the console an integer that you'd like to divide, and that's 2int. Try reading another integer that you'd like to divide, and then 2int. Either of those could fail with a number format exception when you try and convert them to int, because somebody could put Fred in or something like that. And then the result, we do for x from dividend, y from divisor, yield x divided by y. Okay? And then we can say the problem match, if it's success, then we print the result out and we return success. And if it's a failure, it just says that wasn't an int. So basically, when we do this, without the try around it, we would have just said x equals console readline 2int, and y equals console readline 2int. And if either of those had failed, we'd get an exception thrown. But if they didn't, we'd be able to just say x divided by y is the result. The for lets us basically just take the fact that they're in a try, stick it in a for comprehension, and kind of magically evaporate that difference. By putting them in a for, we say get the value from this and the value from this, yield the result just like we would have done otherwise. It actually takes care of what the container needs to take care of for us. So the fact that either of these causes us a failure, the overall result will be a failure. It doesn't matter where it is because of that for. But if it works, it will yield a success. If they're both successes coming in, the semantics of that flat map operation already say, well, the result of a success and a success is a success. The result of a failure and a success is a failure. The result of a success and a failure is a failure. That's built into the container, so we don't have to worry about it. And that's the beauty of these monads, is they give you this stuff for free. So that's that. Now for the demo. And I've really got some time on this. So this is why it matters. Let's have a look at this. So and this is my very contrived demo. I thought about going out to the internet and using real web, real web services. The problem with that was, first of all, it's DevOps, and the network always goes down when you most need it. And second of all, it's actually kind of hard to find a simple, you spend so much time just trying to find a simple REST API that gives you back a number. So I gave up in the end. So what I did was simulated it instead. Pretend that get temp 1, get temp 2, and get temp 3 all go out to some different weather service and get the current temperature where you are. Okay? And they're all slow. Victor Klang famously kills a kitten whenever anybody puts thread sleep in code. So don't do this for real. This is just demo code. But what I've done to simulate it being slow is I've made it take 2 seconds to return the first temperature, 1.6 seconds to return the second one, and 2.4 seconds to return the third one. And then down here, we've got another couple of very difficult calculations that take an enormously long time, we pretend. So the first one takes a second to give us the average back, and the third one takes a second to figure out whether the compare value and the control value are within a certain percentage of one another that you provide. And both of these take a second. All of these are slow operations, so what do? We create futures out of them. We don't do them right here. We say, you know what, don't bother me with the details, just go off and do this, and I'll pick it up when you're done. Don't block my thread doing it. So that's what those are. Now for the actual implementations. So let's take them in order. So test, Scala, hello spec. Right, let's do the first one. This is the naive one, okay? So we've got these futures, and we're like, well, what do I do with this? I can't add things together or multiply things when they're in a future. I'll just wait for the results to come in. So what you do is you sit there, and on each one you say await result. You give it 10 seconds timeout. If it doesn't come in after that, we'll get an exception. Things are sad. But we're actually going to get the temperature out of this. We're going to wait for it to come out of this operation. Then we're going to get the next one, and then we're going to get the next one. Then now we've got all three of those. We can calculate the average, and that's another future. So we will wait the result of that. And now we've got the average, we can calculate whether it's within a percent of the average for each of these temperatures. So again, we're going to wait for all of these. And you see my results are my careful testing. The first one is not within, I think I set the percentage to be 2% at the top. Yeah, the percent is 2. You also see I've got a time it up there, which I use to time the things to sort of show you how this really affects the runtime. So the first one's going to fail, and the other two are going to be within 2%. So I happen to have run it over here already. So if I go down to, not run, test. Test. Actually, it's under compile, the timing. There we go. So if I go back, here we go. I'll show you the first one here. You can say inner test 1. Okay, so inside test 1, I should have shown you that on the, go back really quick. What I've done for each one is timed it. I've nested an inner timing around the bit that constructs the work to do. And then, as you'll see in the next test, there's an outer timer which actually runs that. In the first case, because we're blocking on everything, there's no need to run it or wait for anything. So the times are going to be the same. And that's what we see over here is we see that it takes 10.056 seconds, which is the accumulated time of all of those different weights, plus a little bit for calculation. That's how long it takes to get to the end of our inner part of that code. Okay? And then, strangely enough, the outer code is almost exactly the same time because it's not doing anything. There's nothing else that's done there. Now, this is where it gets interesting. So the second one, and what I said about the 4 expressions is that, and remember 4 just rewrites itself to flat map and map, and I'll show you how that expands out at the end. But what we do here is, instead of waiting for all of these things, we just say for each of the items, get me the temperature 1. All of this is within the 4 expression. Get me T1, get me T2, get me T3, get me the average of these. Get me whether they're within 1, within 2, within 3, within the percentage of them. And then finally, yield a sequence of within 1, within 2, within 3. And now, that's the inner test. That's the setup for the work to do. So that's off and running now, and it's off and running in another future. What's happened with this is, even though there's like 7 different futures here, because of the nature of flat map, we end up with 1 future of result because they're all flat mapped over each other. Okay? So we've got one future, and it's going to have a result in it at some point. That's the setup, and then outside of that inner timer, inside of the outer timer, we now wait for up to a minute for the results to come in, and then we check that those results should be false, true, true. Okay, now let's see what that does to the timing. Okay, so this is inner test 2. 0.0 seconds spent in the setup of that. Basically, it sets up that work, it sets it going, and we're done. Okay, we can carry on with our processing. We haven't blocked. We're on to the next thing. We're sending more work out to more things to be done. Okay, parallel heaven. And when we come out of it, we still have to wait for that. Now, the thing is, each one of those is a flat map. And so the semantics of that are, it's going to wait for each one before it kicks off the next one. In the code, it says, oops, no, don't do that. It says, get temp 1, hello get temp 1. That starts the process. That starts the future of getting temp 1. When that's completed, the flat map's called, and then it gets temp 2. And then when that's completed, it gets temp 3. So each of these futures are chained. They don't happen at the same time. They're one after the other. So what we do now, and you could see that because it took 10 seconds to run. It took the same amount of time to run. Now, if we initialize the get temperatures outside of the for expression, now they can all start at the same time. They all start a future, so they don't block. So we start all 3 of them at the same time. We still got futures. We can still grab the items out of them one by one here, and then we get the average on them. The average is still going to wait for those 3 to come in, but those 3 are going to be coming in simultaneously. So we should save some time there, right? Yeah? Okay, so let's look. And our compile time for that one says, okay, test 3. Again, 0.0 seconds to set it up. 6.4 seconds now to run the whole thing. We've saved 3 and 3.6 seconds or whatever, which is because all 3 of those are running together, and it's the slowest one, the last one to come in, that triggers the next phase. Okay, looking at that though, can we do better? So let's go back to the code. We have to wait for T1, T2, and T3 to come in before we can call the average method. Okay, everybody agree on that. We can't call that until those values are actually available to us. So we have to wait for those. They're latched on that. But once we've got the average, the within percents can actually be done in parallel again, right? They don't depend on one another. So we could fire all 3 of those off at the same time. And there's a very nice construct for that. And this is available, I think, in the, pretty sure it's available in the composable futures too, which is called sequence. And what sequence does is it lets you create a sequence of futures, okay? And what it very cleverly does with its, bit of magic and type signatury is it's a future of sequence of things. It swaps over, it's a sequence of future of things. It swaps those 2 around. So you end up with a future of a sequence of things. Okay? And they're all running in parallel, so basically it builds up a sequence inside and gives you a single future back. So we can kick off all 3 of those within percents at the same time. They're all running parallel now. We end up with a sequence of futures, because each one of these is a future, but then we call sequence on it and it flips it. So now we've got a single future with our sequence of results in it. And that's our withins. At the end, we can just yield that, because what we want back is a sequence of those booleans, whether they're within the percent. And that one runs down here. And to see that to see the effect that has, and I'll run these afterwards so you believe that it's not just text on a screen. That one is down to 4.4 seconds now. We've shaved another 2 seconds off of it by running those 3 things in parallel. So this is how you can really affect things, by using, these monads and knowing your libraries to be able to use things like sequence, and there's another one called transform. These are really good things to know. And then finally, I promised I'd say this, Scala rewrites these into maps and flat maps. You can do this in Java 8 with the composable futures, and it will look something like this. It's not as pretty, but you can figure it out. So at the top here, this is our 3 futures that are started off, kicked off at the same time. They're all running in parallel. Then we say TF1 flat map, and then we get T1. TF2 flat map, we get T2. TF3 flat map, we get T3. All 3 of these are in scope now. Now we call the average on the sequence of T1, T2, and T3. We flat map over the result of that one, okay? And we get average in. And now we can still do our future sequence. We've now got T1, T2, T3, and average in scope. So we can say our percent value, T1 average, T2 average, T3 average. That results in the same thing. So that is equivalent code to what we saw in the for. It's not that unclear. It's just that for makes it a little bit more palatable to look at. All right, I think... I promised you I'd run it, so I will run it. It takes about half a minute to run. So let's do it. Test, start, and then we'll look at the compile view and you'll see it do its thing over here, hopefully. There we go, we're off, running. It's got to find all the tests. Right, I've got 5 minutes left, so let's go to questions while it's doing this. Here you can see they're starting to come in. So, any questions? Because that's really it. Yeah?
Are the futures from Finagle or Scala native?
Are the futures, sorry, what was the first?
From Finagle.
Oh, and are they from Finagle or Scala native? Scala native is a difficult concept because pretty much everything in Scala that's not core language is in a library somewhere. But these futures that I'm using are futures from the Scala core libraries. There are also implementations in Finagle, as you mentioned, and Scala Z has their own futures as well, which are then used to build up things like tasks. They all run roughly the same way, and they all have a flat map that satisfies the type signature. So, you know, the implementation details just vary a bit. So there you see the same result of me running that stuff. Let me just close out with the last slide, which I must put up there, which is summary. There we go. I've got to remind you guys about Scala days, so I thought I'd leave that up there. All right, so I've got 4 minutes left for questions, and then I'm happy to talk at the end. Yes, I see a hand. Yep. So you're asking about sequence, future.sequence? Yeah. So what it's actually for, I think, yeah, that's a monad switch, but what it does, so the question is it a pattern that you see that you get more and more of these kind of things like sequence that operate on monads like that? And the answer is yes. That's actually the kind of ultimate goal of this whole generic programming approach, is when you create something that is a monad, for example, and obeys the monad laws, this is what Scala Z is all about, then you can write functions like sequence that work on any monad of another monad. Okay? And because they follow those laws, you can always switch them. So you can have just a sequence that is nothing to do with future. It's just a monad sequence, and it's, you know, monad A on the outside, monad B on the inside. Sequence will switch them, and it will work because of this kind of, you know, this adherence to the laws. So. I couldn't quite hear all of that, so. Okay, so you're saying, right, so you're saying that it's insufficient, and I would agree, it's insufficient to stop at just knowing what monads are, but you have to know them before you can go to the next level. So, yeah, I mean, this is starting a learning process, which, if you guys are interested, will continue, and it will continue, I mean, geez, it's, you know, this stuff's still being worked out a lot of the time, so it will continue for a long time. The point is, nothing you saw here requires you to actually know the mechanics of a monad to get that for expression that I showed you at the end working with futures. It's a curiosity. People like to know how it works, but it doesn't stop you actually doing that if you just want to use them and trust the fact that they've been implemented correctly. Sometimes they haven't been implemented correctly. That's the difficulty with that, but usually they are. Yeah?
Hello, Bill. I just want your opinion on the following. And I go back to the basics of functional programming where you say it's all about preferential transparency.
Okay.
Now, you, in your 3 different examples at the end, you substituted a val for its expression definition, and the result was not the same. So, to a certain extent, futures are not referentially transparent.
I need to see what you mean, I think.
So, in your first example and the second example, where you replaced the expression, your last example with the 3 vals.
Okay, code. The last example with this one?
Yes, so there, if you replace TF1 by its definition, if you replace TF2 by its definition, if you replace TF3 by its definition, it's another result. So is that not kind of...
you see, so that's a great question. I think what you're saying is the values inside those futures can be different, right? So therefore, the result of that for expression is different, right? It's not referentially transparent. That is actually not correct, okay? The futures themselves haven't been resolved yet. What you get back is not a result, it's another future result, and it will always be the same. If you said val x equals 4 there, the result will always be the same thing. It's not until you run it, it's not until you evaluate it, that the expression changes, okay? So it's purely functional up until the point where we await the result there. And that's the thing. So up until that point, for the vowels, everything like that, referentially transparent. When we push it and say we need a result, then it has to resolve down into, it's like Schrodinger's cat. Is the cat alive or dead? At some point we need to know. But before that, it's the same result. Okay? That was a good question, though. I think we're out of time, but I'm happy to take this. I hope it was useful. It's fun to learn this stuff, and it's not that scary. That's, I think, what I really wanted people to take away is it's not too scary, this stuff. Not when you cut through all of the category theory stuff. So thank you. Thank you for coming.